Hey everyone, I'm super excited to be here to talk about the work we did on distillation and oral fine-tuning to push the capabilities of Gemma 3 models. So I guess we'll cover a broad range of topics, but if you're interested about math, coding, and reasoning, this is the talk for you. So okay, I know a lot of presentations were covered already, so you've seen these details, but just to recap, here are the stages of Gemma 3 post-training. We start by distillation, and then we go into oral fine-tuning. So Louis did an amazing job covering oral HF before, so I'll just talk about the two other flavors of reinforcement learning objectives we optimize in order to get the boost I mentioned. Okay, so let me start with distillation and give you a bit of motivation. So first, Morgan already covered in detail what distillation means and how it works. So here, I'm going to focus on the motivation in the post-training phase. The motivation is we want to extract as much knowledge as possible from the best-in-class models that we have. And this covers a lot of ground. It covers capabilities including chat, math, coding, multilinguality, multimodality, and many others. To sum it up, the point of distillation is to serve as the best initialization possible for the further phase that is oral fine-tuning. Let me now dive into one of the two flavors of oral objective that we want to maximize. And here's one that is specifically tailored for mathematical problems, or problems where we know the ground truth in advance. So one of these problems is represented here. It's a pretty tough problem on divisibility, so you feel free to give it a go, but it's quite tough. If we give it to, say, Gemma 3 27b, right, it's going to output a response that will look like the one represented here. Sure, then some pretty lengthy detailed explanation of the result, and finally the final answer, which is here 110. From that, it's pretty straightforward to do answer extraction and get 110 as the answer from the model. Then we get to the interesting part. We want to do what's called symbolic matching to check if the answer is correct or not. This is for data sets where we have ground truth, remember. And the problem is we cannot just do string matching, right? Because the model could say, hey, the answer is 110.0. Or just or give a fraction that can be broken down to 110, etc. So with symbolic matching, we're actually able to match ground truths even if the strings are different, and this covers much more complex use cases than presented here, like trigonometrical expressions or simple functional expressions. Once it's done, we essentially know if the model output the right answer or not. And we're able to derive, in a very straightforward way, a reward that's going to be positive if the model gave the right answer and negative otherwise. So you might wonder, why do we do that? The reason was summarized by Louis in the previous presentations. It's reward hacking. Here, we have a signal that's very hard, if possible at all, to hack. The reason is that the model simply has to provide the right answer in order to get positive signal from the reward function. And this is why we use it. We use this kind of reward functions to really push the mathematical abilities of our models. The second flavor of objective, which will look very similar, is essentially the same idea applied to code. Suppose you have a coding query. Here is going to be, provide me a snippet that will calculate the entropy of EEG records saved under TSV format. If we give that problem to Gemma 3 27b, it's going to respond as, OK, here's the code, here's the breakdown, here's how to use it. Fine. It's very easy to extract the code, compile it if it's in a compiled language, and then essentially what we do is we throw a bunch of unit tests at the code from the model. We have pre-specified inputs and outputs, so we know what the model code, how it should behave. And again, it's quite straightforward to derive a reward function that will encourage the model to pass all unit tests and to have like functional code. Same thing, super hard to hack because, well, the model doesn't know the unit tests in advance, so it cannot prepare for the unit tests at hand. So I think I gave you a good overview of the post-training recipe we had for Gemma 3, but now I want to dive a bit deeper into performance. I think that's one of the reasons you're here, right? So first, on a pretty diverse set of benchmarks, ranging from knowledge to coding to reasoning to STEM to factuality and so on, you can see that the Gemma 3 models, the 27B being illustrated here, represent a significant improvement over the Gemma 2 family across the board. So this is good. But I want to dive maybe in one area where we made significant progress, which is math. So here we will compare to a much harder baseline, which is Gemini 1.5 Pro, which is a much larger model, right? And you can see that we are able to match or actually outperform Gemini 1.5 Pro on two benchmarks. So math is competition-level math academic benchmark that you might know. And hidden math is our much harder internal benchmark that is unleaked to the models. Let's talk about coding next. Here, we selected essentially 3 representative benchmarks. The first two are, or MBPP and Human Eval, are about Python coding. But N2C, which is an internal benchmark we use, covers 5 different languages. So Python, Java, JavaScript, Go, and C++. So it's more diverse. And again, you can see that comparing Gemma 3 to Gemma 2 shows the level of improvements we've made on coding overall. Finally, I want to dive a bit on reasoning benchmarks. By reasoning here, I mean non-math reasoning, right? Like textual reasoning, like super hard textual queries that require to have an actual reasoning process for the model. The 2 benchmarks we select here are Big Bench Hard and Big Bench Extra Hard. So you might know the first one. It covers from causal understanding to disambiguation to super hard logical thinking. And actually, the Big Bench Extra Hard benchmark takes it even further by adding long context and complexifying all the topics overall. So again, I'm super happy to show you the results and say that we outperform the Gemma 2 line of models by a significant margin here. So it's the end of my presentation, but the key takeaway I wanted to make here is that in Gemma 3, we were able to demonstrate significant gains in math, coding, and reasoning via distillation and oral fine-tuning. Thank you.